In this video, we're going to see one more example of how convolution and the properties of convolution that we saw in the previous video can help us to solve certain types of equations. The equation that we're going to solve here is called an Integro differential equation, which sounds terrible, but we know what differential equations are, but what happens when we throw in this integro part to it? Well, it's exactly what it sounds like. It means it's an equation that can involve derivatives or integrals of a function. All right, so any equation involving derivatives and integrals of some unknown function is called an integro differential equation. I have an example here. We've got some unknown function, y of t. And here we don't have any derivatives showing up. I don't have a y prime. I just have this function y of t. And I have this integral, sine of t minus b times y of v. Now, if you look at this integral, you'll recognize, based on our definition of convolution, this is the convolution of the sine function with the function y of t. Okay, so let's rewrite this in terms of the convolution. So I have y of t plus 3 times the convolution of sine of t with y of t. All right, and when we see this type of equation, our goal in solving this thing is to find out what function y of t works here. And we can take advantage of what we know about Laplace transforms and convolutions to help solve this equation. Now, notice this equation did not involve any derivatives. So I guess you could just say that this is an integral equation of some sort. There's other examples in the book where maybe instead of a y of t, you have a y prime of t. And so you have some combination of derivatives and integrals showing up. But again, we know how Laplace transforms behave with derivatives, and so they can still help us solve those equations as well. Here, if we take the Laplace transform on both sides, let's let the Laplace transform of y of t, like we've done before, let's just call that capital Y of s. And remember in our last video, we saw this property of Laplace transforms and convolution that says that the Laplace transform of a convolution of functions equals the product of their individual Laplace transforms. So I'd have capital F times capital G, if capital F and capital G are the Laplace transforms of lowercase f and g. All right, so let's take advantage of that here. If I take the Laplace transform of both sides, the Laplace transform of y of t is capital Y of s. And now using this theorem here, the Laplace transform of the convolution of sine times y of t is the product of their Laplace transforms. And we know what the Laplace transform of sine of t is from our table. It's 1 over s squared plus 1 times the Laplace transform of y of t, which we're calling capital Y of s. We also know the Laplace transform of t, again, straight from our table. The Laplace transform of t is 1 over s squared. And then just like we've done in our previous equations, we solve for capital Y of s. If I factor capital Y out, I'm left with 1 plus 3 over s squared plus 1. And something I might want to do here is let's go ahead and combine this into one single fraction. That's, if I rewrite 1 with a common denominator s squared plus 1, that's s squared plus 1 over s squared plus 1. And then plus 3 over s squared plus 1. So s squared plus 1 plus 3, that's s squared plus 4. So I have y of s times s squared plus 4 over s squared plus 1 equals 1 over s squared. Divide both sides by this, or multiply by its reciprocal, and we get y of s equals s squared plus 1 over s squared times s squared plus 4. Okay, if we look at this here, you'll notice that this is a situation where we might want to try partial fractions, because I've got a quadratic on top, and then I've got, this would be a 4th degree polynomial on bottom. So I should be able to split this up into fractions some way. And since this bottom is already factored as much as possible, we already kind of know what this would look like. This would be some number over s. I've got a repeated linear factor of s. So first I need to do s to the first power, and then some other number times s to the second power. And then I've got this factor s squared plus 4. And always keep in mind, when your factor is quadratic on bottom, then you need a linear term on top, not just a constant, but this would be a linear function, cs plus d. I'm not going to go through the partial fractions here, but what you end up with is you would get that a is 0, b is 1/4, c is 0, d is 3/4. You can double check that on your own if you like. So what this turns into is 1/4 times 1 over s squared plus 3/4 times 1 over s squared plus 4. All right, now let me just let me make a little extra space to finish this up. All right, so where we are right now is we have capital Y of s equals exactly what we got after our partial fraction decomposition down here in the corner. 1/4, 1 over s squared, plus 3/4 times 1 over s squared plus 4. And if you look at your table of Laplace transforms, this s squared plus 4, that's s squared plus 2 squared. I would like to have a 2 on top. Down here, I have a 1 on top. So if I'm going to put a 2 here, I need to compensate for it by putting a 2 in the denominator as well. So this 3/4 will turn into a 3/8. Right, so 2 and 8 reduced to 4, and we haven't changed anything. I just rewrote this in a way where I can read off my inverse Laplace transform easily. All right, so then taking the inverse Laplace transform to get my final answer, y of t equals the inverse Laplace transform of everything we have on the right-hand side. So then our final solution, y of t equals 1/4 times the inverse Laplace transform of 1 over s squared, which is just t, plus 3/8 times the inverse Laplace transform of 2 over s squared plus 2 squared. That's sine of 2t. All right, so here's the solution to our Integro differential equation, or Integro equation, I guess. There's no derivatives showing up in this one. And you can double check this if I do. So kind of like what we do with regular differential equations, if we want to check our answer, we can plug it in. I can do this function, y of t, plus 3 times this integral. And after I do all this simplifying on the left-hand side, it should just give me a t. All right, so this is just one more application of convolution along with Laplace transforms, and this will finish out chapter 7 for us. Next week, we have a little bit that we're going to talk about in chapter 8 to finish out the semester, and then we'll also start talking about what to expect from the final exam.